So welcome to the talk about cache effect, the hidden cost of memory misses. Now, this is a bit of a update on what's going on in the tracing side of things and the tracing front end in the CTT Cloud extension working group, sorry. But I'm going to just take a step back and I'm going to just ask, the sharing is working, right?
Yes, it is.
Okay, I see it on, yes, perfect. Okay, so what is tracing? Basically, it's a way to figure out some performance issues. It's a way to figure out some races. It's a troubleshooting technique that is very useful to be done in conjunction with debugging. And in this talk, we are going to be exploring how cache sizes will affect your performance, but not your KPIs. Why? So this is also going to be giving you some basic indications, because quite often people will just make dashboards, and the dashboards will look green, but the app will feel slow. So we're going to show how to figure out these hidden stalls. We're going to be doing a deep dive in a few tools, namely Trace Compass, or Eclipse Trace Compass, and the Eclipse Trace Event Logger. But there is TypeScript, and we do have some tracing facilities for TypeScript too that we wanted to share very quickly. Before really starting, though, who are we? My name is Matthew Khouzam. I'm a tracing and performance enthusiast, contributor, maintainer, co-lead, and project owner to many open source tracing tools as well. I have a lot of experience diagnosing real-world performance issues, and we have An here.
Hi, my name is An. I'm a software intern at Ericsson, and I do performance analysis along with full stack software development. For the past few months, I've been developing the tracing tools. Myself is an open source contributor.
I'm excellent. I'm going to just do a little just going to say Ericsson, what we're doing with tracing, we've been actively contributing to the tracing ecosystem for over 15 years. We have partnerships with the École Polytechnique University and with many industries. We support the development of Trace Compass. We use it internally for software and hardware troubleshooting. We help industries adopt tracing in production. And honestly, Ericsson pays me to make the world a better place through free and open source software. I am internally grateful. Fun little fact also, these slides were written in Theia using Theia AI. So let's go into the tracing landscape. There's a lot going on here. Let's say you want to go into the Linux kernel. You're going to have a lot of system level tracing. This will give you an idea of what's going on the ground level. And this will record everything, and then you will open it up with a visualizer later. So you could use ftrace, you can use perf, eBPF, LTTNG kernel tracing. In the user space domain, you can use stuff like LTTNG UST. Then there's uprobes and uftrace. In Windows, there's event tracing. There's the Windows Performance Analyzer, and there's perfview. It's actually a pretty nice combo. Mac OS, you have dtrace, instruments, and OSLog. In Java, you can use LTNG UST Java Agent, JFR, which I do know that the Eclipse Foundation uses and speeds up the ID with, and the Trace Event Logger, which Trace Compass has used to speed things up. And in TypeScript, it's a little more complicated because there's a lot of, the standard is not yet really established. First off, we have OpenTelemetry.js. It's pretty much the industry standard. It's beautiful. It works well if you're at millisecond level. If you have janks, if you're at the microsecond level, it's problematic. Chrome Dev Tools, built-in profiling. And guess what? Mark used it for Jupyter. It actually works really well. Node.js Inspect has a V8 profiler. And you also have some custom JSON tracers. But there's no equivalent to instrumenting tracing that has the kind of simplicity that you put it once and you know that it's always there. So in terms of visualization, There's a lot of tools out there too. I'm going to start skimming over it because I know we're going to get lost in the details, but Perfetto is beautiful. That's the Chrome tracer. We have OpenTelemetry, which a lot of people use too. And of course, there is Eclipse Trace Compass. And for all the really cool people that have gray beards, we have the command line where you can use grep set awk. So now, coming up to the trace event logger, this is a Java style tracer that is UST or L2TNG UST user space tracing inspired. It's lightweight. It has easy integration, but it has fewer features than UST. Now, I'm going to say a hot take. Fewer features is a feature, not a bug. Because you can make scopes where you have one span that goes under another. You can make flows so that you can have asynchronous calls that are traced. You can have counters, and you can have lifespans. And you can also have stuff like instant. But this is pretty much it. And because of the fact that we're forcing people to think about how they want to display their data in the tracing, it makes the analysis much easier. It also makes your tracing more efficient because by having a purpose-driven tracing, you are not going to be recording useless data. And this is basically tracing semantics that I'm describing. You define what you want to trace, what you want to see, and you don't get partial data. When you say, I want to trace a begin, you get the end. So in TypeScript, we have a similar approach. This is something that we have instrumented our code with. And I'm going to just show you very quickly the code. Here's your code that you might have, like a cache processor. And then you import a trace logger, and you can see the way that it's done here. You make a span, and when you exit the span, it exits. Then with this, I'm going to just scroll down very quickly. You'll see that at the end, you push all your events, and it would be pretty good, pretty accurate, and exception-proof. And I believe this, I hand over, oh no, this one, oh, excuse me. The design of Trace Compass, you will see it looks an awful lot like an FFmpeg or some kind of data processing flow. It's very modular. You can make a trace parser and replace one. You can make an analysis. You can add one. You can have a state system, which is a cache on disk. So the analysis is what calculates what events came in and makes states. A state is a 2D event where you have a time begin, time end, and you know that you're in a certain state. And then you have data providers, which will read the analysis and read your state system. And these will be queried by the views. So the view can say, give me the CPU usage of core 23 between 2 and 3 a.m. and give me 1,000 samples. It will give that. So I believe this would be on yours.
So since Trace Compass has such a modular design, we're able to kind of integrate it into a lot of modern tools. So for example, we have the Theia trace extension and the VS Code trace extension, which is built on the trace server protocol Node.js client. And we also have a trace server protocol open API documentation, which is really cool because not only you can interact with the trace server using the Node.js client in something like React or using the Theia IDE, you could also build a Python client library, for example. And the trace extension sits on on any extension host. So we have Theia IDE, we have VS Code, any other VS Code flavored editor like Cursor or VS Codium. And these are available through the OpenVSX marketplace and the VS Code marketplace. And underneath it all, we have we do request to a standalone Java trace server through HTTP and in that way, we can fetch traces, perform analysis, and have the results feedback into the trace extension. And we continuously are porting over features to the extension from the Eclipse Trace Compass. And one of those latest additions is the flame graph. And we cannot talk about flame graph without talking about flame charts. So what is a flame graph? Flame graph is used for aggregated profiling. The flame chart is used for time-aligned stacks. And using both together complementarily would give you perspectives on your application performance. So for the flame graph, the stack traces collapsed and is sorted by frequency. So you can see an illustration screenshot there to the right. And it kind of looks like shark fins when you view it in the flame graph. For the x-axis, it's a percentage of samples. So your width would be equivalent to the time you spent on running that method or functions in your application. For the y-axis, it gives you the call stack depth. So let's say you have a recursive function, it will go all the way down to the to the simplest case. And for it's best for finding hotspots and CPU bound bottlenecks. It loses the with that it loses the temporal information and also the execution order, which is where the flame chart comes in. The flame chart looks pretty much the same, but it's actually represents stack traces over time. So you have a chronological order of your function executions. And in the x-axis is the time progression instead of the samples. In the y-axis is still the call stack depth. It's best for understanding execution flow, cache misses, I/O waits. So you would have a blocking process that's taking like 5 seconds. You would know that. So when things happen, you know the duration patterns. So I'll give it back to Matthew.
Okay, so why are both of these features useful for cache analysis? Flame graphs are really useful for bandwidth. Basically, this is going to show you your overall performance. But then, flame charts will show you stalls. It will show you janks. So cache misses are a temporal pattern. You need the flame chart for it, but the flame graph will show you where to look in the flame chart. So here's an example of both of them in action, or a flame chart in action. This one is pretty fun. If you notice on GitHub, I sign all my commits. I have a little verified. Mikhail Barbaro will be proud of me. But someone asked me, gee, doesn't that slow you down? So I got to check out the Git code, which is really fun because you get to git clone Git. And then I instrumented it, and I looked at the difference in performance. It is 30 milliseconds slower. I will accept removing that much of my life to make sure that people are confident that if I say it's from me, it's at least from my computer. And another thing, for all of those with the benefit of flash photography, Anne made an amazing video explaining flame graphs and flame charts. It is really worth the view. In fact, I'm going to copy this and just paste it in the chat right now. Enjoy. Okay. So the new VS Code trace extension feature is that combo. I am thrilled about the killer combo. And I just want to put here where you can also check out the code if you want. And yeah, it's the same backend. And therefore, it's going to be offering the same, I would say, pedantic level of performance that Trace Compass offers, but with the modern ID experience that Theia offers. So let's get to a real example. And this is an example that I anonymized thanks to a former lead of Theia. He is a lead of Theia. He's just a little less active these days, Marc Dumais. We debugged this together. There was this service that had caches, and the caches are synchronous, and they had many threads reading from them. Now, the threads were competing for reading, and they were all reading sequentially in the same access pattern. That sounds perfect for caches, right? And when you look at your cache hit rate, you have 100 threads reading, and you have a hit rate of 100%. You can't get better than that. In reality, it was slow as heck and infuriating. All our dashboards, our latency metrics, our throughput metrics, they're all perfect, 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 but it is unusable. We are trying to reconcile that problem. So we did instrumentation on the server, and the static instrumentation is always available. It is a low overhead instrumentation, it's high precision, and the cool thing is that when it's disabled, it's basically if false, so there's minimal performance perturbation. Let's have some code examples. The original code is this. This looks a lot like the TypeScript code, doesn't it? Then the next code instrumented is this. We added these lines, and in our try, we added a resource, a try with resource. And so it automatically writes all the entries and all the exits, including exits from exceptions. So the code results are that we showed the delays at the cache boundaries, and we're able to visualize the synchronous calls. This is really cool to me. You see here, we have all of our functions, and please note that this is our call stack, so our stack versus time. It is a flame chart, not a flame graph. And every one of these calls, I'm going to say that they are about 10 milliseconds long. They are not, but I'm just doing that for illustration purposes. This is an uncached time. And you'll notice here that you have a blue area. This is about 1,000 calls that happened immediately. And this is because this item was cached. And then your cache made it super fast until it didn't. Because at this point, we are synchronized. This is fetching for this. This one is fetching for this one, and so on and so forth. So because of that, and here we have an even better illustration, even more of the items are being cached. You basically have what's called a lockstep effect. All the servers all of the requests are happening at the same time, and they are filling up the cache continuously. Now, regarding this, how can we solve it? I can first of all show you that in a much deeper analysis, you have the same problem that happens. And this is from a real world, this is the real world server where the names have been anonymized. Please note in Theia, CG Cloud Blueprint. This happened, so the solution for this is that your caches are poorly dimensioned for your workload. I would very strongly recommend, if you ever see a pattern like this, make your caches bigger. And you need your cache to be able to hold the entire data set, because you read it once, and this is the kind of data that gets constantly refreshed. This is the kind that you need in your memory. Try to compromise and find something else that's slower, or that doesn't need to be continuously in memory, especially read in a synchronous way, and use that way. And I skipped ahead because I was too excited. The synchronous cache misses means that it's a synchronous operation. It freezes your thread. Your correctness is intact. This is really good. Your data is always good. It's just slow. So previously, we were showing with tracing the cause, not just the symptom. This leads to something of a breather, and I did want to give time for questions, so I am going fast here. Do you remember the previous slides where I was showing all the standards for tracing? Yeah. We are not trying to be the 15th standard. We want to work with everyone. We want to help. And I just, in case there are some people that like management radar style plots, if you have two viewers and they have different features, we work together and we deliver the best of both worlds to everyone. We would love to collaborate on unifying everything. So what are the takeaways here? First off, high-level KPIs are really good, but they can be misleading. Secondly, when you do tracing, you will see the bottlenecks. The cache effects definitely have to be contextualized. You have to understand what your software is doing. You can't just say, add more cache and the problem goes away. You need to know what your cache is being used for. So finally, if you have Trace Compass and Trace Event Logger or whichever logger you want, you will see that you'll get some much better insights in the tracing or in your performance profiles. So yeah, I figured that there's a lot of people that are much smarter than me in this room also. I wanted to get the ball rolling and ask a question myself. Do you have any good KPIs, bad performance stories you want to share?
You can go ahead and look at the chat there and see if there's anybody that is
Yeah,
answering that. You're able to view the chat as well, right, Matthew?
Yes.
Okay. Let's see.
Okay, so let's see.
But we do have
Winkler.
questions.
Okay, the first one is from Matthew Khouzam, and he says, how do you generate slides with Theia AI? I want a demo. Now, I have a problem. I'm on a little dinky laptop here. I have at home a big beefy GPU. And so what I do is I open Theia, and in the HTML editor, I ask it to make a Reveal.js slide deck, and I have a Theia agent that I programmed with the template for Ericsson slides. And with that, it auto-generates, and then afterwards, I just go on a rambling rant about what I want to say, and I press enter, and then I get up and I go for coffee, but by the time I stand up, it's already generated, so then I have to sit down and see the results. And yeah, it's really good results so far. Lexono Adianto, I hope I got the name right. What is the overhead of instrumentation? That is an excellent, excellent question. It depends, because we're engineers, and the answer is always it depends. The trace event logger is super studied in terms of its overhead. I believe that our maximum, the overhead for an individual trace point is in the nanosecond range, where I believe that we're able to get like 14 million events a second. And this is because we are IO bound. If you give me a better hard drive, we'll go faster. But you see there's several overheads. There's CPU overhead, and that one we have not really hit yet. But let's say something really powerful like LTTNG, you're going to have about a 2% overhead. Something like perf typically will get a 3%. ftrace will get you in the 2%. Then UFtrace a little more, like in the 5-10. But these are rules of thumb, assuming like 100% usage and all these weird variables. You have to understand that there's a overhead in time, and it just goes and adds on to everything else. So, yeah, I would say low is the answer that I would give a manager, and 50 nanoseconds is the answer I would give my peer.